Hey everyone. We will continue the discussion on OFDM and let us see what are uh, the things involved. Okay, so you can see actually we start with some X number of COM symbols. Okay, and say with the bandwidth P, then we will divide it into L number of subcarriers, where L is the number of IFFT points. Okay, usually some people prefer it as N, right? That's what we have. Suppose I take a 16-point IFFT, then the entire bandwidth will be divided by 16. You will get 16 subcarriers. You will get 16 subcarriers of very minute width. That's what this is. Okay, the number of FFT point is L. Once you take the IFFT, as I told you, for our convenience, we want some cyclic prefix. We want some cyclic prefix. And this cyclic prefix, by the way, is decided by the amount of time delay spread that is there in the channel and the amount of guard. Okay, that is why this guard bits. Okay, that's why the G term here is used. Okay, for the cyclic prefix. Of course, there is a overhead involved. That is why your actual bandwidth you can see, even though you reduce the speed, but then the total number of bandwidth still remains same B. And the number of cyclic prefix, by the way, that adds to the additional bandwidth. Then you do the digital to analog conversion, and then afterwards you use your suitable carrier and you have a signal. Okay. Huh? What next? Okay. So you can see if at all I say take a 1024.50. Okay, now you just respect the massive size of the IFFT FFT that is used here. Okay, this is a typical one standard in LTE which is using 10 megahertz. Okay, which is using a transmission bandwidth of 10 megahertz. You know, there are several variations, but this is one of them. And you can see what author is telling. The transmission channel bandwidth is 10 megahertz and the FFT points which is 1024, out of which 600 of them carry the actual data. Okay, and this 1024 will be broken into 1000 divided by 10,000, 10 megahertz divided by 1024. The spacing between the individual orthogonal subcarriers. Remember, if at all I divide 10 mega by 1024, I'm expecting some number 10, right? But you can see the carriers are overlapping with each other. That is why even though their individual bandwidths are 10, the subcarrier spacing you can see is 15 kilohertz. Okay, subcarrier spacing is 15 kilohertz, and it's a standard. Okay, it's a standard. For the same transmission of bandwidth of 10 megahertz, you do not have the freedom to go for a 512 FFT or a 256 FFT. The subcarrier spacing always remains constant at 15 kilohertz in LTE, that is 4G standard. Okay, one more thing you can see is the cyclic prefix. Okay, they say it is a percentage of L, the percentage of 1024, which is 0.07, which turns out to be 72 number of symbols. Okay, 72 number of guard symbols. Okay, or the guard time turns out to be 4.7 or 5.2 microseconds. Okay, so the sample time, whatever they say, is 32.55 nanosecond for individual sample. Okay, and the guard time is 5.2 microseconds. Okay, one OFDM symbol which will contain several of samples of 32.55 nanosecond each is around 142.7 microsecond. 142.7 microsecond is the OFDM symbol time, out of which 5.2 microseconds or 4.7 microseconds are simply wasted, not wasted, are overhead for the cyclic prefix. So that adds to certain loss, but it's a necessary evil, so you cannot avoid it. Okay, so one thing is for sure, whenever you send some data, there are lots of overheads. So you can see here, out of 1024, only 600 are the actual data, remaining all your pilots, synchronization, and all those things. Okay, as you saw in earlier channel cases. Okay, so remember these numbers. We will revisit them in the next module somewhere. Okay, so here is one more problem. Just go through it. Okay, so it's in the print, it's in textbook only. So what is it talking about here, by the way? So a typical data rate turns out to be, you can see for a 10 megahertz carrier, it turns out to be 21.9 Mbps. Okay, 21.9 Mbps for this very examples, which are where there are actually 600 data carriers. Okay, so what can possibly go wrong, by the way? So whenever you're going for OFDM, of course, OFDM is a tool for you to tackle fading. So by now you might have got an idea why did we go for OFDM. Why did we take IFFT? Because we wanted to convert the frequency selective channel into a frequency flat channel. Remember, so that is what we wanted to do. You can see here, we take you to the beginning. What we wanted to do is, this is our old school data transmission in my GSM, a very large bandwidth data. You put it on a wire, but then different frequencies suffer different amount of fading, the entire channel data going bad. So you take IFFT so that you have this individual very narrow width channels, individual narrow width data, which will fit in a bandwidth less than your coherence bandwidth, so that you can tackle the errors easily by going for error control coding, frequency domain equalization, all such stuff. So this whole method is used for tackling the fading. Okay, for tackling multipath fading. Okay, so this comes at a cost. Okay, this entire thing comes at a cost. Your center frequency, by the way, still remains same at around at center of this entire bandwidth B, but your individual carriers now, but your individual subcarriers, what they call, are very closely spaced. Okay, very closely spaced. So what are the problems now? What sort of problems may occur? Let us see. So timing and frequency synchronization issues are the concern here. Timing and frequency synchronization issues are concerned. So what can happen with the timing synchronization? So what can possibly happen is, you have your data being transmitted, and then afterwards there can be a change in there can be a phase lead or phase lag. Okay, there can be a phase lead or phase lag. This can affect your data reception. This can affect your data reception. And how bad is it, by the way? As and when. Okay, so you can see there is a loss of SNR loss he has given. So what he says is, it is not acceptable. It is not acceptable if at all there are any timing synchronization issues. Okay, so timing synchronization is, suppose at the transmitter there is a that the data is being transmitted at 400 megahertz carrier frequency. At receiver also you have tuned to 400 megahertz, but the data is not in phase, right? There is some phase lead or phase lag, and you have a problem. So it is fine as long as, you can see, it is fine as long as whatever the lead or lag that is happening is within TG and TM, where TG is the guard time and TM is the maximum channel delay spread. Okay, so that is why they have kept some amount of guard time also. So things should be fine. Okay, so as you can see here, what do they say? SNR decreases quadratically with timing offset. That means as and when the timing offset becomes more, signal quality reduces. Then how to tackle it? Longer wavelength signals are increasingly immune. That means reduce the speed. If at all your phase is not matching, if at all timing synchron is not matching, reduce the speed. Longer wavelength signals symbols means slow wavelength signals are increasingly immune. That means more subcarriers, instead of going for a say 1024.50, you go for a 2048.50. It should be much better. But then there are other problems. We will see what they are. Okay, timing synchronizers are not that critical, right? Timing synchronizers are not that critical as long as the induced phase change is corrected. That means you go for a better PLL, phase lock loop, things should be fine. But the real culprit is the next topic, the frequency synchronization. So what is this frequency synchronization? Earlier, you had your bandwidth. you had your bandwidth, comparable to your carrier frequency. But now you are having not a single band with a single center frequency, but there are so many smaller lobes, right? The subcarriers, which are orthogonal to each other. What is orthogonal, by the way? Now see here, suppose at this particular line, you can see here, all these carriers have overlap with each other. You see here, this is indicating overlap. But if at all I choose properly at the center, you can see at this particular point, all contribution from all the neighboring subcarriers has gone zero here. That means if at all you want to receive, you better have your subcarrier frequency tuned at this particular FC only, then only. If at all you go little here and there, you can see in this particular case, you can see, although you have your original frequency data at that particular point, you can see here is the culprit. You have the contribution from the neighboring, this guy here or this guy here, non-zero. Okay. Now that's a concern. Now, when does that happen, by the way? That happens whenever there is a change in the carrier frequency at the receiver or the data itself. That happens due to Doppler. Okay, this happens due to Doppler or the frequency offset. Say you are traveling in a car and say you are at a carrier frequency of 900 megahertz. What's going to happen? Say it becomes 900.01 megahertz because your vehicle is moving towards the mobile user, or it is moving away, right? Away from the tower or towards the tower due to Doppler, and that is called as the frequency offset. And the more closer the subcarriers are, the more is the concern, because for the same carrier frequency, for the same center carrier frequency, if at all I use a 8-point DFT, the subcarriers will be very far spaced from each other, whereas if at all you use 1024.50, the subcarriers are much closely spaced to each other, right? But I chose this because I wanted my channel to be resilient to fading, so I cannot complain. Okay, as I see here, there is one big expression probably which you may have to by heart and write, but then here this is the bottom line. SNR decreases. SNR decreasing is not a good thing. Okay, so this is bad. SNR decreases quadratically with the frequency offset. Okay, SNR decreases quadratically with number of subcarriers. So this is what is limiting us from using higher FFT points. So 1024 is the maximum FFT points that we use. Actually, you go for higher FFT points, it's much more sensitive to Doppler shifts, and you cannot use it for vehicular communication, so and so. Loss and SNR is proportional to SNR itself. So this is what limits. Okay, so this particular frequency synchronization, it actually limits the number of FFT points that you can use. Okay, so that's that. One more very important issue, by the way, is peak to average power ratio. In this particular books, it is given as peak to average ratio. In most of the literature, we find the word peak to average power ratio. And let me tell you, peak to average power ratio is the very reason why the second enabling technology SCFTE is being used in 4G. The reason for the whole SCFDE is peak to average power ratio. Let us see what this particular thing is. Now you can see here, so if at all you are trying to bias an amplifier, right? Because let us acknowledge the fact that the two major issues whenever you are doing the telephony, the bills that occur are, one is the initial bid, whatever you pay for getting a particular bandwidth in the auction site and government. The second thing is your power bills, because it is the power amplifier near the towers, which is the second most critical thing in any telephone communication, where you incur losses. Okay, so how it is supposed to be, by the way, a typical power amplifier with the response will be something like this, and you are supposed to have the whole the thing biased in the linear region only, as and when you move towards this non-linear region, there is going to be more data loss from input to output. In linear region only, it is fine. Okay, so there is this term called as input back off, defined by P in saturation divided by P in. We are not interested in this. Let us see what is the real concern. The real concern is sometimes your data, okay, sometimes your data. Now remember, I take my sequence as say 1111. Okay, that is my sequence, which is a usual thing. If at all I'm doing a telephony, you might have seen my voice. Now you are listening to me. I talk, I pause, I talk, I pause. So these pauses say no data. In this particular case, say the all data is a constant. Okay, say I take a value 11111111 and I take an 8-point DFT. What is the answer? 8-point DFT of 11111111 is 8 into delta, right? 8 delta. That means it's a sudden spike. It's a sudden spike. So what happens is, even though your time domain data is having a very low peak to average power ratio. Did you get the value? By the what is peak to average power ratio? Peak to average power ratio is P maximum power divided by the average power. Okay, peak to average power ratio is maximum power divided by average power. And what's going to happen is, if at all your maximum to average power ratio is very high, okay, if your peak power is very high compared to your average power, then you will have to bias your power amplifier in larger region. If at all say I want to drag this particular line further higher here, I want to drag this line further higher here, you can see I will need much more biasing. You remember when you are doing your RC coupled amplifier, right, or your common source amplifier, common drain amplifier in your electronics lab, there are two things. One is the input and output. The second thing is the biasing. The biasing consumes battery. The biasing consumes lot of power. Whether you are sending the data or not, whether you are talking or you are not talking, the biasing always is on and power is always getting consumed. So you want to keep this particular region as small as possible, but then this particular value, very high peak power to average power ratio, is not allowing you to do so. It's a concern, especially when you are using an IFFT. It's a concern, especially you can see there is some content from some website. You can read this from this side. You can pause and you can read maybe later. Okay, so it's a PAPR is a concern. The reason why this happens is, even though whatever you speak is having a very low peak to average power ratio, the moment you take an FFT Fourier transform, the value is going to increase. As I said to you, if at all I have 8 ones and I take an FFT, my answer is going to be suddenly an 8 at 0, right? If at all, imagine if at all I got a 1024 point FFT of a sequence 11111111, right? All 1024 ones, and I take a 1024 FFT, then I am going to have a very large value of 1024, right? It's a concern. It's a concern. So the moment you take FFT, you handle to the, you tackle fading very nicely, but then peak to average power ratio is a concern, and somehow it needs to be tackled. You can see higher value of FFT makes it much worse. What is this curve, by the way? This curve, you can see at input there is at x-axis there is peak to average power ratio, peak to average ratio in dB, and this is the probability you can see here of peak to average ratio greater than the current value. That means there is a probability of 10 to the power minus 2, 1 in 100 times that my peak to power ratio is more than 8 dB, or 1 in 10,000 times that my peak to power ratio, average power ratio, is more than 10 dB. Okay, that's what this curve is. CCDF, complementary cumulative distribution function. CDF, PDFs, right? Probability distribution functions. If at all you go on accumulating them, you get a CDF, cumulative distribution function. 1 minus CDF gives you CCDF, which starts from 0, all values accumulated, with all the possibilities. Okay, so which is a better one, by the way. So me as a low power, specialization engineer, I would suggest to go for this particular curve. The farther the closer it moves to this particular side, it is always better. As and when it moves away towards this right side, it is not a good indication. But then 1024 point DFT is a norm, right? Because fading is also an important issue. You want to save on your a power amplifier, battery charges, but then you have to suffer fading. Any solutions, by the way? People thought, how do we tackle this? Then suggestions came such that, somebody suggested, if at all, you can see there are 500 samples, right? You can see there are 512 samples, and how many are giving you unusual amplitudes? Say 1, 2, 3, 4 are, say, giving unusual amplitudes. You can see how occasionally they are occurring. Okay, occasionally they are occurring. What if I simply clip this, right? Say anything above 14, anything above 14, I will make it to 14, or anything about 12, I make it to 12. Oh, what's going to happen, by the way, if at all I do that? See here, very rarely there is a value 16.5, and then very rarely there is a value 15, 15.5, and so on and so on. What I will do is, I will clip anything above 14 to 14. Is that a concern, by the way? Will it affect? So what may happen possibly? My data may go wrong, but then I have my error control codes, right? Block codes, convolution codes, they will take care. Out of 512 values, say some 4 to 5 values are going wrong, error control codes will take care. Okay, so that should be fine. It will reduce my electricity bills, right? It will reduce my electricity bills as a service provider, and it will allow me to, tackle fading also. So that's what people thought. PAPR is a problem, so they thought, let us go for clipping. Let us go for clipping. All the values above A, let us simply clip it. All the values below A, let us retain them. Let us one idea. But then what it happens is, whenever you do this particular sudden transition, sudden cutting certain values, then they tend to, increase the spectrum. They tend to increase the spectrum. Anything square, sudden changes, they increase usually the spectrum. And when they increase spectrum, then it is going to go into the adjacent frequency, again causing issues. So spectral regrowth, that's what it is called as, and it is supposedly not a good thing to do. So clipping, by the way, was thought to be not a good idea. Clipping was not to be not a good idea. You can see here, here this, as and when you decide to, have this value of A, cut off. Let us cut this particular A. Let us make it from 16 or 15 or 14 or 13. As and when you go on compromising, what's going to happen? Your bit error rate is going to go much more worse. Okay, this is not a good thing. Standard is 10 to the power minus 4 or 10 to the power minus 5. You can see things are going much worse here. So clipping was the earlier very, very trivial idea suggested, and it did not work out. Okay, then there have been so many literatures, by the way, of how to tackle PAPR, and a very clever suggestion came in the form of this particular thing called as single carrier frequency domain equalization, which we'll speak in the next video. Let me stop here.